All right, we're in the last section of chapter 14, section 14.8, change of variables, Jacobians. So let's remember back in Calc 1, when we integrated the integral from a to b of f of g of x times g prime of x dx, we used a u substitution here. So we called this u and this du to rewrite this as the integral from, say, e to d of f of u du, where u was our g of x. And so we want to do something similar for our double and triple integrals. So we want to be able to take a double integral, say over region R of f of xy dA, and rewrite it as a double integral over region S that's determined by some functions g of uv, h of uv, times this term that we're going to call the Jacobian. So it's the absolute value of partial with respect to x of u, partial of x with respect to u times partial of y with respect to v minus partial y with respect to u times partial x with respect to v du dv. And this extra term here is called the Jacobian. All right, so this is our goal. If x is g of uv and y is h of uv, then the Jacobian is denoted with the partial of x comma y over partial u comma v is the determinant of the 2 by 2 matrix, partial of x with respect to u, partial of x with respect to v across the top, partial of y with respect to u, partial y with respect to v across the bottom. And that gives us exactly what we saw above. Okay. So that's where that comes from. Let's make sure that we can find that. So let's think about converting to polar coordinates. That's a change of coordinates. So let's find the Jacobian for the change of variables defined by x equals r cosine theta and y equals r sine theta. Well, we're going to fill out this matrix. So instead of uv, what I have is an r theta. Okay, so in the first row, I first want the partial of x with respect to r. That's just going to be cosine theta. And then partial of x with respect to theta is negative r sine theta. And now in the second row, I have partial of y with respect to r. That's just sine theta. And then partial of y with respect to theta. That's going to give me r cosine theta. And I'm going to take that determinant. So I get r cosine squared theta when I multiply down this diagonal. And then minus the product down that diagonal. So minus negative r sine squared theta. But I can factor the r out. So I just have r times cosine squared theta plus sine squared theta. And that's our favorite trig identity, right? That's just r times 1 which is just r. And that's exactly our change of variables. If I'm integrating over region r and I switch to a polar region, it's f of r cosine theta r sine theta times r dr d theta. So that's where that r came from a few sections ago. In general, we're going to have a change of variables given by a transformation t from S to R. So S is the UV plane, a region in the UV plane. R is a region in the XY plane. Where T of some point UV gives you the point X comma Y. Where XY is given by some G of UV for X and H of UV for Y. So again, if we think back to our polar coordinates, we're looking at T of R theta, and that's defined to be R cosine theta comma R sine theta. Right, that's our X and our Y. All right, I'm going to let you try finding a Jacobian and then we'll do an example.